Welcome to the Ex Terra Podcast. The Ex Terra mission is to explore and discuss the business of space and its effect on the national and global economy, as well as life on Earth. How does what happens in space affect your life every day? That's what we're exploring on the Ex Terra website, as well as on this podcast. My guest is Dan Klopp, Director of Marketing and Business Development for Space Systems at ILC Dover. ILC Dover is part of the team led by prime contractor Collins Aerospace, which was one of two teams awarded contracts by NASA for next-generation spacesuits for both the Artemis program and the ISS. Dan, welcome to the program.
Thank you, Tom. It's a pleasure to be here.
And it was an exciting week for you and the other contractors when NASA picked the teams for the new spacesuits. What was the selection process like?
Well, the request for proposal came out last September, and there was then a period where we could ask some questions and put our proposal together. The first round of proposals were due, I think, 2 weeks before Christmas. So we had an exciting holiday season there with a mad rush right before the Christmas break. And then there was another round of clarifications that happened in April. And then we were sitting on pins and needles waiting to see how the award came out.
And how did you get notified, just out of curiosity?
We typically, in the past, we've been notified 2 to 3 days in advance. In this particular case, because of the timing of the announcement, just after the Memorial Day holiday weekend, we only had about 24 hours advance notice that we were one of the selected companies.
Tell us a little bit about ILC Dover.
So ILC Dover has a rich history that goes back to the mid-1930s. It was started at the height of the Depression as International Latex Corporation in upstate New York. At some point in time, the company moved from upstate New York to Dover, Delaware, hence the name ILC Dover. And somewhere along the way, the company developed a consumer products piece and a government contracting piece. And although we don't strictly do just government contract work today, the current company known as ILC Dover is a legacy of the government contracting piece. The other piece of the company was split off years ago and was originally called International Playtex Corporation, but Playtex has been bought and sold many times since then. But we have the same historical roots as Playtex.
So you're not making ladies' undergarments anymore?
No. As I understand it, there was a running joke back in the Apollo era that the same company that made the spacesuits for the Apollo astronauts also made bras and girdles.
Oh, man. So somehow I can see those guys at NASA making that joke.
Yes. Yeah, it wasn't quite true because the split had already happened. But nonetheless, there was an element of truth in it since we have the same historical root.
Give us a little bit about your background, Dan. How did you get into this business?
Oh my gosh, long story. So I have a bizarre educational background. I have undergraduate degrees in physics, chemistry, and math. And then somewhere along the way, I decided I liked business. And so I went and got an MBA with a concentration in marketing. And I've had a very varied career, but for the past 3 years, I've been with ILC Dover, helping with the marketing of their space systems division.
Now, you mentioned a little bit about the history of the company, and part of that has involved pressure suit and spacesuit design and manufacturing that dates back into the 1950s. So take us through some of those highlights as to how the spacesuit designs have evolved and how the company got involved in that.
So the company, as you mentioned, was making pressure garments for high altitude aircraft, specifically spy airplanes. And that then evolved into our spacesuit work. As I understand the history, long before my time with the company bid on the Mercury program, did not win that. Those suits were made by B.F. Goodrich. We bid on the Gemini program did not win that contract. Those suits were made by the David Clark Company. And then we bid on the Apollo program and did win that contract. And we have not lost a contract since then.
So what goes into the design of a spacesuit? I mean, what are some of the considerations that you have to have that make it so that you can win those contracts?
So there are two major components to an EVA spacesuit. One of them is the pressure garment assembly. It's called the PGA. That's the piece that we make. So that's sort of helmet to boots. That's what, when you look at that, you think, oh, that's the spacesuit. But then there's another major component that's made by Collins Aerospace, who's been the prime contractor for years in our relationship. And that's called the PLIS, the Portable Life Support System. It's the backpack. So it's, and you put those two pieces together and they make what NASA refers to as an SSA, a spacesuit assembly. So that's the PGA plus the PLIS makes the SSA. So for us and our side of the engineering, the considerations and what makes it challenging are that it's a full pressure garment. So when you pressurize it, it gets very stiff, but maintaining mobility and dexterity with that pressurized garment is the challenge.
And so your specific aspect of this is to design the garment. You've got new suits that are going to be used on both in low Earth orbit on the ISS and also on the moon's surface through the Artemis program. How are those two designs different?
So they're very different based on the application or the mission profile. So the suits we made 50 years ago for the Apollo missions had a very mobile lower torso. They had hard-soled boots, and they were optimized for walking around on the moon. The current design, called the EMU, which is made for the International Space Station, that does not have a mobile lower torso, intentionally designed so, because although we call these events EVA's spacewalks, you're not walking on anything. Your legs are just dangling, and it's actually advantageous to have a fairly stiff lower torso in that design because your legs aren't doing anything anyway. Other than when they're working, a lot of times they will clip their feet into restraints to resist torque when they're doing their maintenance missions on the outside of the ISS. So those are the sort of the major differences between what we call a walk-around suit and what we call a zero-G suit.
Why was it necessary to design new suits for, say, the Artemis program? And I know technology has changed a great deal in the last 50 years, but is it essentially the same design as Apollo astronauts used 50 years ago, or were there a lot of new considerations that you put in place because of the changes in technology?
So quite a few changes from the Apollo suits. One of the designs of the Apollo suits was necessitated by the nature of the spacecrafts and how much mass they could lift back in the day. Those Apollo suits were actually dual purpose spacesuits. They had a removable PLIS, and the spacesuit served both what today we would call a launch entry abort spacesuit, which is a spacesuit designed, worn generally unpressurized, designed to be used in the spacecraft, and only pressurizes in the case of a cabin depressurization. So that's one type of suit that people would call a spacesuit. And then, of course, there's the EVA suits, the suits where the spacesuit becomes a miniature personalized spacecraft for the duration of that EVA. So back in the Apollo era, those were dual-purpose suits. So they were an all-soft design. And then fast forward into the Space Shuttle International Space Station era, those suits have a hard upper torso. They were designed to minimize shoulder injuries for handling large pieces of space equipment that was coming out of the cargo bay of the space shuttle. And if one of those, although there's no weight in space, things still have mass, and because they have mass, they have momentum. So those suits were designed so that if a satellite or some piece of the International Space Station were to start to get out of control, coming out of the cargo bay, that an astronaut could reach out with their gloved hand and stop that satellite and resist that that momentum that it had, and that necessitated this hard upper torso design. Fast forward to the suits we'll be building under this new NASA contract. We're going with what we call a hybrid upper torso design. It takes the best elements of a hard upper torso and a soft upper torso and combines those together into an architecture which allows extreme resizing. One of the good parts about a hard upper torso design is just what I was saying before. It provides a very stiff structure and minimizes shoulder injuries if part of the mission profile is to restrain something that's moving, that's pretty heavy. That proved, although it was a NASA requirement that they put on us back in the 80s when we designed the current EMU, it proved never to be a big problem. So that requirement is not part of this new suit design moving forward. And by going away from a hard upper torso, what that allows us to do is design in a lot of resizability into a single size upper torso.
And we'll talk about that a little bit later on in the podcast, but I want to dig just a touch deeper about some of the challenges that astronauts face when they're outside their spacecraft. What are some of the safety things that you have to take into consideration when you design, as you said, basically a personal spaceship?
So the things that are design considerations for us for an EVA spacesuit are sort of in order of priority is, first of all, air pressure, has to maintain pressure, has to provide oxygen to breathe, and subsequently also scrub the CO2 that you exhale. It has to provide thermal protection. The temperature extremes in space are quite stunning. If you're in direct line of sight of the sun, it's very, very hot, hotter than any point on Earth. And if you're in the shadow, where you have no direct line of sight with the sun, for instance, in low Earth orbit, when you're on the dark side of the Earth from the perspective of the sun, it's very cold. So you have to protect against those temperature extremes. Another consideration is micrometeoroid protection. Mm-hmm. There are tiny pieces of space dust that are flying at just incredibly high velocities. And if you remember back to your high school physics, kinetic energy is 1/2 mv squared. Mm-hmm. So although the mass is very low, you're taking half of that term anyway, but you're squaring the velocity term. And at the speeds that these pieces of space dust fly, it gives them the total kinetic energy pretty close to a high-powered bullet here on Earth. Mm. So the whole exterior layer of a space suit, an EVA spacesuit, is essentially a bulletproof vest. So you have to prevent against those penetrations by that, and also dissipate the energy from that so that it isn't transferred to the astronaut's skin and cause a bruise. And then, of course, there's radiation protection. And those considerations are a little different for deep space or lunar than for low Earth orbit. But nevertheless, you're dealing with forms of radiation that we just don't see here on Earth because our atmosphere protects us against those.
You know, when I told a friend of mine that I was doing this interview with you, and of course, the story that always comes up is John Glenn sitting famously on top of the Mercury capsule. And I know this wasn't one of your suits, but he was sitting there waiting to launch, and as they say, needed to relieve himself, and they hadn't taken that into account when they designed the suit. I'm sure that's something that has been addressed in the intervening 60 years or so.
Yes, and that's changed actually from the Apollo era to what we do today. So the suits we made for Apollo, the consideration there was a catheter, which is not a very comfortable way to perform those functions. And today's suit, we use what's called a MAG. So NASA loves their acronyms. MAG stands for Maximum Absorbency Garment. The joke that we have when somebody asks, how does one relieve themselves when they're on a spacewalk, is we say, it depends.
It depends. I'm talking with Dan Klopp, Director of Marketing and Business Development for Space Systems at ILC Dover. Take a moment right now and click on subscribe to make sure you don't miss any of our podcasts, or if you're watching on YouTube, any of the videos from Ex Terra, the Journal of Space Commerce. Dan, at the press conference in Houston, there was a lot of talk about the adjustability components that allow you to create just a few variations of the suit to accommodate all possible astronauts. You touched on this a little bit earlier, but what challenges did that present?
So going back to that hard upper torso design, the problem with that from a resizability standpoint is that hard upper torso absolutely locates the shoulder bearings, because they're set into a fiberglass shell that is the hard upper torso. So in order to accommodate a lot of different size astronauts, you have to have different size upper torsos, because that shoulder bearing is absolutely a critical dimension on the suit. Because the suits are a modular design, things like arms and lower torsos can clip in and clip out of a standard upper torso design that includes an integrated PLIS with that. So it's relatively easy to resize components like arms and gloves. And the resizing actually is a bit of a misnomer. It's just using a different component and clipping it in. But that fundamental architecture of the upper torso, if it's based on a hard upper torso, you're locked into a very limited range of sizes that will fit in that specific upper torso. So then to accommodate a big range, you need multiple upper torsos. This hybrid design that we've come up with allows you to relocate the shoulder bearings within this exoskeleton sort of upper torso. And that, with a tiny pile of that I can hold in the palms of my hands, a tiny pile of resizing components with just two sizes of upper torso, we can fit now with this new design from the first percentile of humanity up to the 99th percentile. Whereas the current upper torso design, this hard upper torso design in the current EMU, with three sizes of upper torso, we figure fits from about the 40th percentile up to about the 85th percentile of humans. So but that takes three upper torsos to do that, and it's a pretty limited range. Whereas this new design with two upper torsos, we can fit from the first to the 99th percentile.
Does that alleviate the necessity of designing suits specifically for men and women?
Yes, it's well known that women tend to be smaller than men. So not that there aren't very small men out there as well, but this first percentile to 99th percentile in terms of numbers that Americans would recognize in terms of feet and inches is just under 5 foot tall at the first percentile, up to about 6'5" at the 99th percentile. So by having just these two upper torsos with these resizing components, which, by the way, we designed so that they could be swapped out without tools, therefore can be done easily in orbit or on station on the moon, that we can accommodate a whole wide range of humanity, from very small females to very large males.
Does that also kind of do away with the necessity of, I'm sure it makes it easier to transport a bunch of components as opposed to a whole bunch of different suits as far as space is concerned, weight is concerned, those things, when you are concerned about the energy that it takes to lift it all out of the gravity well.
Right. That's one of the real strengths of our design, is that total mass to station to cover over the length of a program. So over the length of the Artemis missions, which could go on for decades. The total mass to station, total mass that you have to get out of the Earth's gravity well up to the moon, is much, much less with this resizable design than it would be with a hard upper torso design.
One of the criticisms of the Artemis program and some of the delays that have been mentioned have been that the spacesuit design has kind of maybe not been on track as well as it could have been. Does this contract award now help put companies back on track as far as getting NASA the suits that they need to maybe put Artemis a little bit closer to back on track as far as their launch schedule is concerned?
Yes, we believe so. The spacesuit that NASA put out there, their what they called their reference design back in near the end of 2019, that at that point they were calling the xEMU. That was based on a development contract that ILC Dover had with NASA on a suit that was, at the time that we delivered it, was called Z2 back in 2016. And we, independent of that NASA development contract, not long after we finished up our work on Z2, we started a internally funded research and development on this new design that we're proposing now. That's part of the xEVAS contract, the contract that was awarded to us and to our competitor last week. And so we've been developing that design with our own internal research and development dollars for years now. And that's what's culminated now in this design that was part of our proposal.
You've talked a little bit about this already, but I want to, again, go just a shade deeper on the fact that you're one of two contractors that have been selected to provide the Ascent entry suits on the CTS-100 Starliner. What are some of the significant differences between the Ascent entry suits, the AES suits, and the EVA suits?
So I touched on this much earlier in our discussion, but Ascent entry suits, which that's the acronym that Boeing uses. The acronym that NASA used to use in the space shuttle era was ACES, ACES. The acronym that we use internally for those type of suits are LEA, launch entry abort. But those are suits that are designed to only be used in the spacecraft. And ideally, those suits spend their entire life unpressurized. So they're a full pressure garment, but they only pressurize in the case of a cabin depressurization. So the way the way I like to characterize that type of suit is that it's sort of like the seatbelt in your car. You put it on every time you get in your car, but you cross your fingers and hope that it doesn't have to do its job. Because if it does have to do its job, you're having a bad day. Well, similar to the launch entry abort or AES type of spacesuit, those are an emergency garment that are designed to be pressurized, but only for short periods of time. They do not have an independent life support system, so they don't have a PLIS, so they're not capable of going outside the spacecraft. And they tie into an emergency life support system that's inside the spacecraft. So they have umbilicals, short hoses that go from the emergency life support system in the spacecraft to the suit. And again, they ideally spend their entire life unpressurized, but they are a full pressure garment. So they don't provide the mobility and dexterity that a EVA spacesuit does, and they also don't have the associated PLIS, the big life support backpack.
The other component that ILC Dover was involved in with the CTS-100 was the airbags that cushion its landing. Talk about that a little bit.
So we've done quite a few development projects with NASA over the years on inflatable accelerators and other types of inflatable space structures. And as a result of that work, Boeing contacted us years ago when they started the Starliner program to develop the landing airbags for that. Boeing decided to go down the path of landing the spacecraft on Earth, on terra firma, on land, because saltwater is a very corrosive environment. So if you go all the way back to the capsules back in the Mercury, Gemini, and Apollo era, they landed in the ocean, but those were not reusable spacecraft. They were sort of a one-time use. And it's very difficult to reuse a spacecraft that lands in the ocean because of the corrosive nature of saltwater. So Boeing decided to land those on land. Of the two orbital flight tests they've done so far, they both landed at White Sands Missile Range in New Mexico. And it's that those landing airbags deploy several thousand feet in the air after the drogue parachute and the three main parachutes have slowed the craft significantly. And they just provide that sort of final soft landing when the craft comes to Earth.
You're working with Sierra Space as well on Orbital Reef. What's ILC Dover's role in that project?
So our role in that is to build the structures that are part of the inflatable habitats piece, what Sierra Space calls LIFE. They have an acronym for those inflatable habitats. And again, with our expertise in inflatable soft structures, going all the way back to the 50s and the pressure suits that we were making for the Air Force, it's an inflatable structure that takes the place of a hard-walled structure in space. And the advantage to an inflatable structure is you get much more living volume for a given amount of mass and volume that you have to launch into orbit. So by putting inflatable structures as part of Orbital Reef, with far fewer trips to orbit to put all the pieces of the space station in orbit, you can get much bigger living volume.
Is that perhaps the foreseeable future of space stations? Do you think is going to be a move more towards the inflatable type habitats as opposed to the hard structures?
Yes, we believe so. Obviously, we have a lot of expertise there, so I have maybe a somewhat biased opinion there. But I can tell you that we are doing work on inflatable structures for not only Sierra Space and Orbital Reef, but for Deep Space Gateway and lunar habitats as well.
What are some of ILC Dover's future plans as you expand your offerings in the commercial space realm?
So,
if you can talk about any of them, I know some of you probably
talk about a little bit. So, part of the reason that we started development on this new generation of spacesuit years before NASA had even put a contract out is we saw a coming need for spacesuits for commercial space, and we see those as kind of having two paths that they might go down. One is just for maintenance missions, much like what is the vast majority of spacewalks that have been done over the past decade on the International Space Station have been maintenance missions. So you need to maintain whatever orbital structure you have, and sometimes that maintenance necessitates doing a spacewalk to get to some component that's on the outside of the orbiting station. So that's one use of commercial space or commercial space suits that we see. And then another use is what I would classify as space tourism.
Okay.
With the growing, as costs come down, there will be more and more people that have sufficient funds to take a trip to space. It is a fascinating, life-changing experience from what I've been told. I've never been to space myself, but I would love to go. But at some point, people are going to want to leave the spacecraft and duplicate these spacewalks that we've seen, because you just get a better view as a space tourist of that. And so that's a whole other use of commercial use of spacesuits, EVA spacesuits that we see. But we envision doing those slightly differently for both safety reasons and sort of overall mission profile. Those will be higher pressure suits to completely eliminate the need for a pre-breathe, which the current suits require a pre-breathe. And it's too much, I think, to ask or expect a space tourist to go through all of that just to go out and have a look-see. So these will be higher pressure suits for space tourists, which will decrease the mobility. But if there's no specific task that they need to perform, if it's just I'm going to go out and take a look at things that I just can't see from inside the spacecraft with this small observation ports, mobility and dexterity aren't as big a deal there, so we can get away with a higher pressure design for those needs.
Sort of the ultimate scenic overlook.
Exactly.
And by the way, I'm there in line with you. If somebody offered me a chance to go to space, I'd jump in a heartbeat. I would go right now. So you and I are of a similar mind on that. Dan, we're just about out of time, but look out, if you would, over the next 10 to 15 years in the realm of space commerce, and tell us kind of what you see in your crystal ball.
We see a very bright future. We see that that there will be, as commercial stations like Orbital Reef, and there are several others that are well into their planning phase, will be in orbit. There will be research that goes on in those, that in a microgravity environment, you can just do things that are simply impossible here on Earth. We see uses for some types of manufacturing that it's advantageous to do in a microgravity environment. And there are other types of manufacturing that having a hard vacuum, so to speak, mere inches away from where you're living, not that we can't recreate those vacuums with extensive pumping kinds of capabilities here on Earth. It's just so much more convenient to do those types of things in space. So there'll be some types of manufacturing that we believe, and a lot of research, both sort of chemical, biological kinds of research, as well as maybe other types.
Well, Dan, we're out of time for the Ex Terra podcast, but thank you so much for joining us. It's been very interesting, and good luck with those suits, and congratulations on your contract award.
Thank you very much, Tom.
Dan Klopp is Director of Marketing and Business Development for Space Systems at ILC Dover. The company is part of the Collins Aerospace team that is one of 2 contractors selected by NASA to design a next-generation spacesuit. That is going to do it for this edition of the Ex Terra podcast. You can subscribe to the audio version of the podcast on Spotify, Apple Podcasts, and many other popular podcasting platforms. Be sure to click on subscribe so you don't miss an episode of the podcast or any of our other videos. You can also get daily space commerce news at xterrajsc.com. And one thing more, be sure to connect with us on LinkedIn and follow us on Twitter at xterrajsc. Until next time, I'm Tom Patton. Thanks for joining us.